how bad it was before. Horn and shank is probably the most common algorithm for vertical flow. This is the ground truth. What you see here is the real movements. Because purple here, you can see that purple means I moved approximately, let's say, 5 or 60 pixels in the y-axis, but only 2 pixels in the x-axis. So the color, if the color is similar, it means they're right. It's a good approximation. Okay.
I don't understand that you don't use 2 images?
I used 2 images.
Ah.
Yes. I only showed one, but the second one is 1 minute after this one. It's just 1 minute after. With downdrafts, and now I'll do that. And this is a segmentation. This is a very good one. Not always it works that well, but this is automatic, of course. I didn't draw it myself. And you see that the lines, the green lines, fall exactly where I wanted them to fall. And all of these methods are going to be available in GitHub and File Exchange. If it's relevant to any of you, you can use it. And this way you can average per cell and get results. I'm going to skip how I did it and move forward. Okay, so we're going back to the idea. We have this layer in which the vertical velocity is decreasing linearly, but the problem is that as you saw, maybe you noticed it in the optical flow images, but usually divergence tends to come in pairs. When you have positive divergence, you have negative divergence next to it. Which means when I'm averaging, I have very weak results. This is why usually the same for updrafts and downdrafts. This is why usually scientists look only at the updrafts, only at the positive vertical velocity and not the negative vertical velocity. And even though the equations I've shown before are not guaranteed anymore when I'm looking at the positive vertical velocity, we still see results, and very good results, and I'll show you. So this is just a demonstration of what happens, of the problem when I'm observing only the positive vertical velocity. I have here 2 different models, and you can see this layer. This tab is the clouds. This is the height. Y-axis is height. Here you have the updraft profile, and these are the clouds. And you see inside the cloud, the linearly is actually the updraft, the positive updraft, 10 meters below the top of the cloud. So the height is the updraft. And the color is the divergence calculated at the top from the model. So the height and the color are not connected, but if you're looking at it, you see a very, very good correlation, which is exactly what we're looking for. And this is just a visual representation of the results you're about to see. It's a little bit small, but we have here 2 models. It's the same model. No, I'm only looking at positive values of the divergence and updraft.
That's called convergence.
No. Convergence is
converged in the problems.
It converges.
No, when it converges, then you have negative.
It's a little top, so it can go only downward.
Yes, you have some, you cannot, you see here scatters, the blue lines are scatters between, it doesn't really matter but because it's too small to see, but the scatter is between the divergence at the top and the positive updraft 10 meters below it, exactly as we've seen before, but this time each blue dot here is the result of this segmentation of the clouds. So it's an average over a segment, and you see the results. And the relationship is very strong. You can't really see the R correlation, but the R correlation is in the area of 0.8, 0.9. And the difference between these two is that here the segmentation is over very large cells, and here it's over the finer fractals of the clouds, which means I have a lot more cells to average on. And still, when you put all of them together, they're very parallel. They're very similar, which is exactly what we wanted to see.
If it's correct that you assume that the maximum vertical velocity is at the base of the cloud?
No.
So I don't understand what is going on here. You assume linear change of the vertical velocity at the top is 0.
Yes.
So the maximum must be at the bottom.
Yes, but it's a layer.
It's
only true until it reaches the bottom of the layer. It doesn't mean the bottom of the cloud. Usually we used to see profiles which goes first the updraft is intensified and then it starts to decrease. So in marine stratiformless, from what we've seen, we see that from the maximal updraft in the cloud, it starts to decrease linearly, all the way to the top.
always from the maximum. It must decrease.
No, but it decreases linearly, which is very nice. So I'll move on. So, okay, we talked about the updraft, which is 10 or 20 meters below the cloud top. This is not our main interest, as you said. We're interested in the cloud base updraft and the maximal updraft in the clouds. So we tried to, for the same models, we did the y-axis is the R correlation, and this axis is how far are we dropping from the top. And you can see the two cases for the finer scale and for the cell scale. And you can see that as we go further down from the top, the R correlation gets worse, which is not good. But this is the result of the fact that the error is not immediately affecting the divergence. It needs time to actually, for example, from the base, it needs time to actually go through all the cloud and spread at the top. And only then I will see the correlation. And in addition, the clouds move horizontally all the time. So I need to measure according to that movement and according to that time lag. So if we take into consideration the time lag and the movement shift, this is divided into W at the top, W at the mid of the cloud or the maximum area. In marine stratiformless, it's in the middle usually, and not the 2/3. And at the base, this is again the autocorrelation, and here we have the time lag. So you can see that at the top, the best results are achieved without a lot of time lag. And as we go further to the maximum updraft and the days, it goes further, and we need more time lag, and the results get better. And the R correlation gets better. The difference here, what you see here, the blue ones are the actual ground truth divergence calculated from the model, and the yellow one is calculated from using epic flow, the optical flow algorithm I talked about. So you see there are differences, but still it's relatively good. And this is a proof that we can actually do it in practice. Okay, so we're talking about practice. We talked about the ship that traveled between Honolulu and Los Angeles. So here you can see an image from GOES 15.
But here I have to interject and say that I didn't believe that there will be anything here, and I told the guy it's a waste of time, and I'm afraid that he sees something interesting. Okay, let's see, I hope that you will surprise me. And he did.
So, yes, thank you. So until now we talked about models in a very fine resolution. The resolution was 50 meters per pixel, and I had the image every minute or every 40 seconds. And here in GOES, the resolution is 1 kilometer per pixel, so it's 20 times worse. And the resolution is every 15 minutes. I have an image. And therefore, Danny didn't think it's going to happen or actually produce something. But we've seen otherwise. So, so I'll just explain what you're seeing down below. This is the green line is the ship's trajectory according to the logs from the ship, where it measured for 2 hours along the way. But we had to do the shift correction. We had to correct. We didn't want to know where the ship was geographically. We wanted to know which clouds it sampled. So this is why we use the optical flow to understand the average movement, the purple movement, like you saw before, the average movement, and we changed the trajectory to the ship track, the red one. So what you're looking at is the ship track, the red one, down here, over 2 hours. And just to emphasize how bad the resolution is, here, what you see here at the beginning of this journey of 2 hours, this is how it looks from the ship. This is a camera on the ship looking above, looking at the clouds from below. And you can see here, actually, you can see fractals, and you can see how the clouds look like. But here you don't really see anything. The resolution is quite bad. For that reason, we did the optical flow and we kept it in pixel level. We didn't average over cells, we didn't use the segmentations because it can't work in this resolution. So, so what you see here in blue is the divergence calculated at each pixel of the red line over 2 hours. The problem is that we have image every 15 minutes. So for example, this section here, until the gap, you have gaps here, it's all from the same 2 images.
Really, that you expected what time between images you are expected to give good results?
I would expect a few hundred meters and 2.5 few minutes.
For just to tell you, the Japanese geostationary satellite, the resolution is 0.5 kilometer now, and the time resolution is 2.5 minutes. So, but Japan is not well known for marines that call us clouds, unfortunately. And I didn't have how to validate my results over the Japanese area because I don't have a ship like I had here in Honolulu. And, but in practice, I hope it would work in geostationary satellites. And the orange lines are the second moment updraft. This line, and the tens where the ship goes, it can change everything. For example, CND, because of the coarse resolution of GS15, I would probably assume that CND have the same, I would calculate the same divergence. The divergence is quite similar. But D would calculate a very, very strong updraft versus C, which will calculate very weak updraft. So this is one example for why a ship is so problematic. If I had dense coverage over the whole area, I would be in a good place. But comparing images to a trajectory of a ship has a lot of problems.
Did you try to look at an optimal problem, correct the ship's trajectory in such a case that we get the maximum correlation or something like that? Inverse problem.
I didn't go all the way that deep to try and correct the trajectory. Just what broke it, what made the breakthrough was moving from the green one to the red ones. When we worked on the green trajectory, we had bad results all the time, and we didn't understand why. and then the shift correction was very promising, but still, I can't really avoid these kind of situations and these problems. And as I told you, I cannot lag here. But all the work we did on the models are very promising, and we think that it would be. I will be able to test my methods on it because I have a time series, because they are all looking at the same grid and they're following one another. And this is going to happen. It's in phase 0 right now. Danny and I attended the kickoff, and the French are really serious, and everybody is serious. it's quite nice. And sorry. So yeah, you see here the simulation of how they're gonna follow the cloud. But I have to admit that my thesis and my work is only secondary here. The main objective is convective clouds, and this is done by a method that I also worked on with Danny's son, Amir Rosenfeld, and he's also, and you have samples all over the world. And I'll just go back. The main